Algebra 2, Lesson 5-3, Graphing Radical Functions. In this lesson, we'll be able to graph and transform radical functions. And the lesson vocabulary is radical function. So let's start with exploring reasoning. Consider the formula for the area of a square. A equals S squared. Graph the function that represents area as a function of side length. So we already know that the area of the square would be side times side. So we're already familiar with this equation. So we're going to explore radical functions using this equation. First of all, we want to graph the function that represents the area as a function of side length. So I'm going to make a table. So this is part A. X and Y. So in this case, your X is side, right? And then Y is area. And so if the side is, let's say -1, but your side cannot be -1 in real life. So we're going to put all the positives and zeros, okay? So when side is 0, which is also not possible, but we're going to start from 0 because anything greater than 0 will work, and we need an endpoint, okay? So when x is equal to 0, obviously a would be 0 because no side length, no area. And then when side length is 1, 1 times 1 is 1. So 1 square units. And then 2 times 2, 4, and then 3 square would be 9, and so on. So we can graph in quadrant 1 because it's going to be positive 1 through 0, 0, and that's going to be 1, 1, and that's going to be 2, 4, and that's going to be 3, 9. Okay. Yeah. And then part B, on the same set of axes, graph the function that represents the side length as a function of area. So now we're going to switch x and y, and we're going to graph the same function, but that represents side length as a function of area. So we're going to solve in terms of s. Using the same function, what is s equal to? Solve for s. Yeah, in terms of area, it's just going to be root a, right? And so our table of values would be the opposite. But remember, your side or area cannot be negative. So let's think about, so in this case, x is going to be a, and then y is going to be s. So we are switching x and y, right? And then, yeah, and so when the area is 0, obviously side is 0. But when the area is 1, side is 1. When area is 2, then it's root 2, right? And then when it's 4, it's 2. When it's 9, it's 3, and so on, if we are trying to find the whole numbers. And so in the same graph, try to picture this. 0, 0, 1, 1 is going to go through the same point. 2, 2 roots, so it's a little bit bigger. But 4, 2, right? So then it's going to be here already. 4, 2, then 9, 3. So you'll see a graph that looks like this. Okay, so the first graph, this one is a equals s squared, and this one is s equals root a graph. Let's look at part C. How are the two graphs related? How are they related? Well, they're the inverse, but let's talk about domain and range. What is the domain? Is this the same? They're all real numbers, but positive, right? Positive real numbers. So the domain of the first is going to be all real numbers greater than 0. And then the other one, all real numbers greater than 0. But is there anything that that would be different? Well, you look at these numbers and they're flipped, right? The domain here is the same as the range here, like 0 to 3 for each each pair of points, right? So then we can say the domain of the first is the range of the second. And then the range of the first is the domain of the second. So this is important because when the domain and range flip, that means we have the square and the roots, right, function. So this is one thing that you have to keep in mind. Square and the root, they're the opposite. They're inverse relationship, right? So let's think about this essential question. How can you use what you know about transformations of functions to graph radical functions? Let's start with example 1. Graph square root and cube root functions. Graph the following functions. What are the domain and range of each function? Is the function increasing or decreasing? So first of all, in order to graph this by hand, you can make a table of values and then graph. So you have 0, 0. When x is 3, it's going to be root 9, so it's 3. When x is 12, it's going to be root 36, and that's going to be 6, and so on. So then you can find some points that are going to be nice little whole numbers, so perfect root, right? Find perfect squares so that you can make perfect squares divided by 3, right? And that would be your x. So for this, you can plot the points and you'll see like a nice little curve. It's not a straight line, right? For square root function, the radican cannot be negative, so your domain is all positive numbers, including 0. So your graph starts here instead of, there's no arrow on the other side, okay? So your graph is always going to be like this, or like that, or like that, or like that, or like that. Yeah. So yeah, your graph may have a curve, but it's only going to have one end behavior. And then the other point is just going to be the end point. So the solution to the square root function always returns a positive value because you always have positive of square root. So the range is also all positive, including 0. So as x increases, what's happening? Y also increases. So the function is increasing overall. So let's look at another example. G of x is cube root of 2x. So how's cube root different from square root? So make a table of values and you'll see that you can have negative values for x and y, right? So if you plug in negative values, you'll be able to get back some negative y's. Yeah, so if the x value is negative, y value also has to be negative. The x value is positive, y value also has to be negative. Yeah. So if you graph it, it's going to look something like this. You're going to see positive side and the negative side. It's like you're putting two square root functions together. And this is still going to be the middle, it's called the inflection point where your direction changes. But this is the important point here in our radical function. Your endpoint, for square root, it's the endpoint, and then for the cube root, it's like the endpoint of the two square root function. So if you divide this in half, it's like the point that's in the middle. It's called the inflection point, and this is a very important point. We'll learn later how to figure this out really quickly. It's like a vertex of your absolute value function, and yeah, you'll be able to tell this point easily from the equation. Let's look at try number 1 first. You're going to graph the following functions in parts A and B. What are the domain and range of each function? Is the function increasing or decreasing? So answer this question, pause the video, and come back when you're ready for answers. Okay, are you ready? Let's look at part A. 1A. You're going to graph this function. In order to graph this, first you have to make a table of values. So when x is 5, graph is 0, and when x is 6, then you have a -1 in the radicand, and that's not a real number, right? Root negative 1 is going to be I. So you're not going to have anything that's that's less than 5, right? 4 minus 5 is -1. Yeah, so nothing less than 4, nothing less than 5. And then you're going to plug in other numbers like 6. 6 minus 5 is 1. And so 6 comma 1, because root 1 is 1. And 9 is a number for a perfect square. So 9 minus 5 makes 4, and that's a perfect square. Root 4 is 2. And then the next one would be 14, comma 3, 21, comma 4, 30, comma 5. Yeah, so you can graph a function that starts at 1, 2, 3, 4, 5, comma 0. And then you have 6, comma 1. And then you have 9, comma 2. And 14, comma 3. And 21, comma 4, and it's like farther away, right? So then you see this graph. Yeah. So 14, comma 3, 9, comma 2. So at least have a table of values or label your graph by points. And then we're going to see if it's increasing or decreasing. And then let's find the domain and range. What's the domain? It is not all positive because 0 to 5 cannot be defined, right? So domain is going to be anything that's greater than or equal to 5. And then range, because of that, well, not because of that, it's still the same as your parent function for your square root, which is all positive numbers including 0. And as x increases, y is increasing even though it's slow. So the graph is increasing. And that's it. Let's look at part B. It's a cube root function. And so part B, you'll also write the table of values when it's we can have negatives, right? So when it's -9, for example, -9 plus 1 is -8, and cube root of -8 would be -2. -2 cube would be -9, right? -8. And so that's 1 point, and then -2 will make it -1, and y would be -1, and then -1 becomes 0, and then 0 comma 1, and then 7 plus 1 makes it 8, and so cube root of 8 would be +2, and 26, 3, and so on. And so if you graph this, it's going to look like this. Okay, so you're going to have -9 comma -2, and -2 comma -1, and then -1 comma 0, 0 comma 1. There's no 0 comma 0. I didn't mean to put that point over there. So this one, and then this one, and 7 comma 2, and 26 comma 3. And so you'll see like the 3 little dots that are clustered here. This is definitely the inflection point, the point in the middle. And then you'll have the half of the function here. So like the graph that looks like a square root is gonna be here, and then the other way over here as well, right? And so this is going to be -9 comma -2, and then we have -2 comma -1, -1 comma 0, 0 comma 1, and 7 comma 2. Okay, so we graphed it. What's our domain? Domain is all real numbers. You can pretty much have anything, right? And then range is also all real numbers. And then the graph is from left to right. It seems like, oh, this is decreasing, that's increasing. No, from left to right is the graph going up or down. So from left to right, this is increasing and that's also increasing. So overall, the graph is increasing. So your radical functions will always have the entire graph increasing or decreasing. It's not like a quadratic function where there's going to be a domain where it's decreasing and then a domain that's increasing. For radical functions, you'll see it's increasing or decreasing throughout the graph. All right, so that was parts A and B for our example 1. Try it. Let's look at concept of radical function. So the radical function has a form of f of x equals a nth root of x minus h and then plus k. So this is also a form where you can easily find the point hk, which is this point right here. So for cube root, it's like the point in the middle, and then for square root, it's the end point. Okay, so hk will be the point, and a is the vertical stretch or compression from your parent function. So looking at this, you can figure out the transformations from your parent function right away. So if your function are not in this form, then you can change it to this form. But if they are in this form already, you can easily picture the graph in your head even before solving anything. So let's look at example 2. Graph a transformation of a radical function. So graph g of x equals 2 root x plus 3 and plus 5. So what transformations map the graph of the parent function root x to the graph of g? How do the domain and range of g differ from those of f? So first of all, we're going to identify a, h, and k. These are called parameters, okay? A, h, and k. And so a is 2, k is negative 3, because remember it's x minus h. So your h is not just positive 3, it's negative 3. K is 5. So you have a point at negative 3 comma 5. That is the endpoint. So you can already picture negative 3 comma 5. Oh, it starts here. And your parent function starts here, right, from 0 comma 0. So there's a translation, horizontal translation 3 units to the left, horizontal translation 5 units up, and then you have a stretch, vertical stretch by a factor of 2. So it may look bigger, like vertically. Yeah. So if you plot the table of values and graph it, you'll see that the parent function starts from 0 and then it looks like this. But g is also stretched vertically, right? Instead of looking like this, like about in the same angle, it stretched vertically. And then it moved 5 units up and then 3 units left. And so how did the domain change? Domain changed from all positive numbers greater than or equal to 0 to everything greater than or equal to negative 3 instead, right? So the translation, your h is going to change your domain. Then your k is going to change your range. So the range now is anything greater than or equal to 5 instead of anything greater than or equal to 0, right? So that's the change of domain and range. And we already know how to say the transformations, right? So let's look at try number 2. Graph g of x equals 1 over 2 root x minus 1 minus 3. What transformations of the graph of f of x equals root x produce the graph of g? What is the effect of the transformations on the domain and range of g? So pause the video, see if you can identify all the transformations, and find the domain and range. Okay, are you ready? Okay, let's look at the graph. So first of all, you need a graph your table of values would be negative. So you have 1 and negative 3. You have 2 and negative 2.5. You have 5, negative 2. 10, negative 1.5. 17, negative 1. 26, negative 0.5. And then you'll see that your h and k is 1 comma negative 3. So you have an endpoint at 1 comma negative 3. And then you have a vertical compression. So it's going to be going up really slowly. So you have 1 comma negative 3. 1 comma negative 3. And then 2 comma negative 2.5. And 5 comma negative 2. And 10 comma 1.5 and stuff like that. Negative 1.5. Yeah, and then so it's going to go up really slowly. You can already see it's a vertical compression, right? So let's describe the transformation. It is compressed vertically. Whoa. Vertically by a factor of 1/2. And then what about h? Yeah, translated 1 unit to the right. 1 unit to the right. And then translated 3 units down. And what about the domain? The domain has been translated horizontally. Let me type so that it's clear. The domain has been translated horizontally by 1 unit to x values greater than equal to 1. Greater than or equal to 1. Yeah. And then the range, oops, spelling error. And then the range has been translated vertically by negative 3 units to values of y greater than or equal to negative 3. Okay, so that was like the answers for try number 2. We'll continue with example 3 in the next video.